So now that we have all the tools that we need to perform differentiation, we're going to talk about how to differentiate inverse functions such as arcsine of x. So just to recap what an inverse function is, let's say we have a function of x equals to 2x plus 1. Now to find the inverse function of this, what we will need to do is to make x the subject and then solve for x in terms of the other function. So the easiest way to do this is we're going to substitute f of x by x, and we're going to substitute x in here by f to the power of minus 1. So it is not actually f to the power of minus 1, but rather the inverse function of x, and that's how it is represented by f minus 1 plus 1. And now we're going to solve for this. So that's going to become f minus 1, or inverse x, is going to be x minus 1 over 2. So that's going to be our inverse function for this one. So that's the general idea behind it. Now, let's say we have a function y equals to arc sine of x. So arc sine is the inverse of sine. How do we go about differentiating this? Well, we know it's not going to be arc cos, because that's just not how it works. So what we can do is we can take the inverse of this, make x the subject in this equation. So we're going to have sine of y equals to x. And from previous videos, we learned how to use implicit differentiation for when we have an expression like this. So if we want to find the derivative of y with respect to x, all we need to do is differentiate both sides with respect to x. So because y is a function of x, we use the chain rule here. So the chain rule tells us that we're going to have the derivative of the outside, which is going to be cosine of y, times the derivative of the inside, which is dy of dx, equals to 1, because the derivative of x with respect to x is 1. So this means that our dy dx term is going to be implicitly a function of y, so cos y. But obviously we don't want a solution that is just in terms of y. We want x terms in here. So what we can do is we can use a trigonometric identity, which is sine squared y plus cos squared y equals to 1, and we can solve for cosine in terms of sine. And the reason for that is our original function is an inverse function of sine, so it makes sense that we want to transform this cosine function into an expression that contains sine function, so that the two cancel out eventually. So if we rearrange the terms in here, we arrive at the relation cos of y is going to be square root of 1 minus sine square y. So we can rewrite this as dy over dx equals to 1 over square root of 1 minus sine square y. And now what happens if we put this expression into y here? Well, that's going to be square root of 1 minus, so this is going to be sine, the argument is going to be arc sine of x, and the whole thing here is going to be squared. So we can work our way from the inside out. So what happens when you have sine and the argument arc sine? Well, these two functions are inverses, so they're going to cancel out, leaving dx by itself, and then dx is going to be squared. So our final derivative is going to be 1 over square root of 1 minus x squared. So that's what the derivative of arc sine is. Now what happens when we want to get the derivative of a function like arc cos? So let's say we have y equals to arc cos y. Well, we would use the same method, and in the end you would actually find, I encourage you to go through the same method to find it using this trigonometric substitution. We would actually get minus 1 over square root of 1 minus x squared. Interestingly enough, The only difference between the derivatives of arc sine and arc cos is just this sine at the front. Much in the same way that the difference between the derivative of sine and cosine is a negative sign at the front. So that cannot really be a coincidence. There's just a relation between the two that is also present in here. Another expression that you might derive is, sorry, I'm going to write this as d over dx of tan x would actually give us 1 over 1 plus x squared. So I encourage you to do this as well. And there are some tables of derivatives that I have included in the description that you can consult to find the derivative of tan in terms of x. But in the end, the general idea is that we can use this method to find expressions for those derivatives. So implicit differentiation and the chain rule play a major role in deriving these expressions. So what we can do now is we can say, well, what do you think is going to be the derivative of some function? So let's say arc sine f of x. What is this going to be equal? Well, if we write this as y equals to arc sine and we try to get the inverse function of this, so let's have f of x equals to sine y. Then we apply the derivatives to both, so that's going to be f prime of x equals to dy over dx cosine of y. Then this is going to lead to dy over dx equals to f prime over x, and we have cosine of y. And we learned from the first example that we just did that this can be replaced by the expression 1 minus the argument of the function squared, so that's going to be fx squared. So we're going to end up with this expression, f prime of x over this. Same applies for arc cos and arc tan. And yeah, I made a mistake in here. So when I said d over dx of tan was equal to 1 plus x squared, I was really wrong. That was not the derivative of tan, that was the derivative of arc tan. So just to rectify that which I just said, this is going to be the derivative of arc tan and not tan. The derivative of tan would be sec squared x. And in general, we can write a formula for this so that we don't have to go through the process of doing this back and forth. The most general formula for finding the derivative of an inverse function is to have 1 over dx dy, which is the derivative of x as a function of y. So how can we use this? Well, let's have arc sine again. We're going to have y equals to arc sine. So if we make x a subject, that's going to be x equals to sine y. Now if we take dx dy, that's going to be cosine of y. And this is going to lead to dy dx equals to 1 over cosine y, which is what we had in the beginning. But this just doing this, applying this formula, basically cuts down the step of using implicit differentiation to rearrange the terms. So it is a bit quicker. So this is the general formula you would use for an inverse function. And this pretty much concludes all the methods that we need to know for differentiation of all types of functions. And in the next video, we're going to cover how to find the derivative of higher order derivatives. So for example, the second derivative of function y, and so on.